and welcome to my talk. Today we deal with a very strange behavior that we see in carbon steels. The behavior was first observed by Meyer in 2009. Here we see one of his experiments. We have a SN diagram, but we don't see the total number of cycles, but only the number of cycles at the high stress amplitude for the VA loading. In CA loading, that's just the same as the number of cycles overall. But in the VA loading, we have two different load steps. And since we have a factor of 100 between the number of cycles at both load steps, we have a factor of 100 between where these load steps lie and where the actual number of cycles is. Now we would expect if the lower load level wouldn't cause any damage or wouldn't benefit the material in any way, then we would expect the black points to lie just in the scatter of the white points. We see at high load levels, where the lower load level is above what's typically or what's traditionally referred to as the fatigue limit, we see that the black points lie on the left side because, of course, the lower load levels also inflict damage. However, if we have lower loads below the so-called endurance limit, we see that the specimens live longer, even only counting the cycles at the high stress amplitude, and that means that the low stress amplitude cycles somehow must benefit the lifetime of the specimens instead of reducing it. This was done in ultrasonic testing, and one may argue that that's an artifact of ultrasonic testing, but that argument is false because our Norbert Schneider did experiments in conventional and in ultrasonic testing, and here we also see in the same diagram the increase of lifetime due to low amplitudes. Here's another study conducted by Anton Kolishkin from Bosch. He took a 50 chromo 4, which didn't have any heat treatment after machining and therefore had some compressive residual stresses at the surface. He did constant amplitude tests just above the so-called fatigue limit at 520 megapascal, and then he combined these 520 megapascal with different variable amplitudes in a two-step test with different lower amplitudes, which were 490, 462, 440, and 410 megapascal. And for the lower ones, which were below 90% of the so-called fatigue limit, he did observe somewhat of a lifetime increase. And as we saw for the other specimen, for the other ones, he observed a reduction of lifetime. Then he did other experiments which are even more interesting because he added holding times. That means he did a constant amplitude test, and after a number of cycles, he stopped the constant amplitude test, held the specimen for a while at different loads, and then after that resumed the constant amplitude tests. The loads were below the higher load of the constant amplitude test, therefore he didn't introduce any further plasticity, and as we're working at room temperature, we really wouldn't expect any influence. However, if the holding stresses were high, we observed a momentous increase in lifetime, which is, of course, the phenomenon that we're talking about today. However, he then annealed the specimens, or annealed other specimens, of course, and did similar tests there. And these specimens didn't have compressive residual stresses at the surface, and therefore, and he then didn't observe any extension of lifetime. So we believe that there's two conditions that are to be met for this phenomenon to occur, which is compressive residual stresses at the surface and lower amplitudes just below or somewhat below the so-called fatigue limit. Now we were, of course, looking for an explanation for this behavior, and we looked to Sinclair's theory that he published in 1952 on coaxing. Coaxing is when you start a fatigue test on a specimen well below the so-called fatigue limit, and you run, for example, for 10 to the 7 cycles, and then you introduce an increasing load step until at one of the load steps the specimen fails. In this way, you get, or in many materials, you get fatigue limits that are well above the traditional or in the typically like the fatigue limit that you would get in a typical test, and that's because you're training the specimens. In Sinclair's theory, the loading at the lower load level creates microplastic deformation, which of course means dislocations. These dislocations promote Cottrell atmospheres, and then at the higher load levels, these Cottrell atmospheres improve fatigue performance. In Sinclair's theory, this extended over different volumes of the specimen within the experiment, but we ignore that part, and then we apply it to constant amplitude loading, and then it's basically that in the first load block we generate dislocations, and then it works the same way as in Sinclair. We get Cottrell atmospheres, and in the later constant amplitude load steps, we have an improved fatigue performance. Now there's still the question why we have an influence of holding stress, because in classical theory, after Fick's law, we don't get any influence of the holding stress on the diffusion behavior, and therefore no influence on the strain aging. However, newer research has shown that we do get an influence of especially of the hydrostatic stress on the diffusion behavior. Here we see 4 unit cells of a BCC crystal, and here we have a carbon atom, and that is supposed to diffuse from here to here. And then this path relates to this path, and as it passes through this path, it has to pass an energy barrier. And simply put, if we pull these specimens here apart, then in this point the carbon atom is closer to further away from the iron atoms, and therefore we need less energy for this diffusion, and therefore the diffusion barrier is lower with higher hydrostatic tensile deformation, and we get more diffusion in the highly stressed state. Now that's the theory. We wanted to validate that for our material. We looked at a material where we know that the effect occurred, and we did tensile tests. The setup was that we had the specimens loaded until 137 kilonewton. That relates to 893 megapascal in the specimen. Then we repeated the loading for a few times to introduce more dislocations. And then in the first test, we reduced the stress to 650 megapascal and held for 5 hours at that value. And in a second test, we reduced it to 6.5 megapascal only and held it for 5 hours as well. And if we didn't have an influence of holding stress on strain aging, then we would get the same results. Here we pull the specimen until it fails. These are the results we got. In blue, we have the holding at 100 kilonewton, and in orange and red, we have, or it's both red here. In orange and red, we have holding at 1 kilonewton. We see how we pulled the specimen over the yield point phenomenon to this point, which relates to the 137 kilonewtons. Then we unloaded and reloaded it for a few times. We held the blue lines at 100 kilonewton and the red lines at 1 kilonewton. And then we pulled until failure. And as we see here, we did see a yield point, another yield point phenomenon. We would expect, if there was no strain aging, these lines to continue like the lines that went there before. And here we have it in a bigger And we see that the stress increase of the specimens that were held at 100 kilonewton is double the stress increase of the specimens that were held at 1 kilonewton. And therefore, we have experimental proof that static stresses do increase strain aging. Now, how do we relate that to the variable amplitude tests, because we don't have any holding times there? We argue that if we have a stress history, we can approximate that with stress increments. And at these stress increments, we always have holding times during which the specimen, during which the carbon inside the specimen can diffuse. This approximation gets very well if we increase the number of increments. And since the debye frequency, which is the frequency in which the atoms attempt to jump, is much higher than the increments we need to get a good approximation, we can assume that we get diffusion, we get a constant diffusion during those increments. However, we have ordering of atoms within the carbon atoms within the crystal due to, for example, the Snug effect. And therefore, the preceding steps influence the diffusion behavior in the following steps. That's where we are now. We need to evaluate further how we can register that in our evaluation, whether we have diffusion or how strong the diffusion is. So today I showed an anomaly that's we have increased lifetime due to variable amplituding loading at low load levels and due to holding times at high stresses. I proposed the hypothesis that is caused by a stress-dependent strain aging. And for variable amplituding, it's also caused by stress-dependent strain aging. Just we have also the additional theory of the incremental holding times. Yeah, and lastly, I showed that the strain aging does depend on stress in 50 chromophore. Yeah, thank you for your attention. I'm looking forward to your questions.
Thank you. Questions?